Welcome back to another lecture from organic chemistry. In last lecture, we were talking about diaxial strain. We said we get this one whenever we put the one substituent bigger than hydrogen in axial position. And that methyl group is going to sense hydrogen that there are 3 carbons far from it. And those hydrogen are in axial position. And because there are 3 carbons far from it, we call it 1 and a 3, okay, 1 and a 3 diaxial strain. Okay, so we have a molecule here, is a cyclohexane, and with 2 substituent. Let's first name it. Okay, so I have a methyl substituent and also tert-butyl. Okay, and the parent is going to be the ring. Why the ring? Because it has 6 carbons. Okay, so this is going to be the parent again because it has 6 carbon. So I'm going to say, let's start labeling it from here. Okay, we're going to call this one 1. Okay, I have 2 substituents, so I need to mention 1 twice. Okay, and which one I need to write it first, methyl or tert-butyl? And we said we don't care about the tert. And so we're going to jump and we focus on B. If I want to alphabetize them, butyl should come first. So on the first carbon, I have tert-butyl. And then again, on the first carbon, I have methyl group. And all these two are sitting on cyclohexane. Okay, sitting on cyclohexane. Okay, so we have 2 substituents there. They are attached to, to first carbon. Okay, the question is, which one is bulkier, the methyl or ethyl? Methyl is a carbon with 3 hydrogens. Okay, so it's a carbon with 3 hydrogen. The tert-butyl, you have a carbon that's hydrogen atoms for it replaced by another methyl group. Okay, so each of this carbon, the new carbon, they will have 3 hydrogen atoms. Okay, which one it will be bulkier? Of course, the tert-butyl, it will be bulkier. So if I want to order them based on size, okay, I'm going to say the tert-butyl, it will be bulkier than methyl group. Okay, now I have 2 substituents, and I want to put them on the chair conformation of cyclohexane. The question is, where should I put them? Okay, so I have 2 options. First option, let's put the methyl down here, okay, and the tert-butyl there. Okay, so we're gonna get CH3 here, and we will put the tert-butyl. The tert-butyl, remember, it has carbon, okay, 3 carbons attached to it, and each carbon it comes with 3 hydrogens. Okay, or I can put the methyl here, say CH3, then put the tert-butyl there. Okay. Now, which one of them is bulkier? Clearly, the tert-butyl is bulkier, and we said it before. Okay. Now, because it's too bulky, very soon it's going to see or feel this 2 axial hydrogen. Okay. So we have 2 axial hydrogen there, and those 2 hydrogens, they're going to see that bulky group, and that's going to create 1 and 3 diaxial strain. Okay, how about the methyl? Of course, the methyl is going to create the same strain, but it's not that strong. Why? Because the methyl group is smaller. Okay, smaller than the tert-butyl. Okay, so I'm going to say again, I'm going to get that 1 and 3. Okay, 1 and 3 diaxial strain. I'm going to get that one, and I do see it in both cases. We see that one. But if you have the tert-butyl in an axial position, it will be way more severe than the methyl group. So if you have 2 groups, okay, 2 groups sitting on 1 carbon, and you wanna figure what's the most stable structure, okay, or the conformation. In this case, put the bulky in equatorial position because it's going to create less repulsion technically, or less strain here. So I'm going to say the second structure, it will be the most stable one. Why? Because it has the bulky group sitting in equatorial position. Forgive me. Okay, because the bulky group in equatorial position is going to be more stable. Okay. Well, here we have the bulky group in axial position, and that's actually the problem, the main problem. this is the trend for the substituent. Okay, ethyl, of course, is going to be bigger than methyl because it has one CH2 more. Okay, and that's going to make it closer to the hydrogen atoms. Okay, now how about the propyl? Okay, propyl versus isopropyl. Propyl is linear. Okay, and the propyl, it will be linear. While isopropyl, this is the shape for isopropyl. Okay, it's like a U shape, and technically it will be like a spherical, shape versus linear shape. The linear shape is going to be, it's going to take less space, and so I'm going to say that one it will create less repulsion. Okay, so from now, let's put it this way: as we increase substituent or the branches on carbon, the repulsion will go up. Okay, repulsion will go up. So as you increase substituent on carbon, repulsion goes up. Okay. Now, how about the butyl? Butyl, you can make it linear. Okay, but if you start branching it, so here instead of attaching from the end, now we are attaching like the butyl from the second carbon. So that means this carbon is going to have technically a methyl group here, and then like an ethyl group there, and it will be attached to wherever. Okay, again, this is going to be a bit bulky. And how about the tertiary butyl? It will be like a spherical, and that's going to be the most bulky actually structure for butyl. Okay, so as you increase the branches on carbon, size of the substituent gets bigger, and it's better to put them in equatorial rather than axial position. Okay, why ethyl is bulkier than methyl? Okay, let's show the methyl. Okay, if I put the methyl in axial position, okay, on purpose, I put it in axial position. Okay, this hydrogen atom, this hydrogen atom is going to sense those two hydrogens, and it will have 1,3 diaxial strength with them. Okay, now what will happen if I extend this bond? Okay, that means we're going to make this hydrogen closer to those. How do we do it? Okay, so instead of putting hydrogen atom here, okay, I'm going to replace one of the hydrogen atom by carbon. Okay, now I have a carbon here, and that carbon is not active. So what do we need to do? We need to add 3 hydrogen atoms to it. Okay, so as you see, the hydrogen atoms, now there are 2 close, okay? 2 close, and I have 1 here, and that's the second one. They will be too close to these 2 hydrogens, and that's going to create huge 1,3 diaxial strength. Okay, so as you increase the size of the substituent gets closer to the hydrogen atoms, and that's going to create a stronger diaxial strength, 1,3 diaxial strength. Okay, so if I want to choose the best position for ethyl or methyl groups, I'm going to put them down here in equatorial position. Okay, so I'm going to put the CH3 down there. Okay, and here I just simply leave it as hydrogen atom, and hydrogen atom is not going to create much 1,3 diaxial strength. Okay, and also for this one, I will put ethyl there. Okay, or I can say pointing this direction. Okay, and hydrogen atom, it will be pointing up. Okay, and so this one, it will be the ethyl, and that was the methyl group, and both ethyl and methyl are in equatorial position. Equatorial position. Let's practice another example. Okay, says we have 1 tert-butyl, okay, and then 4 methyl cyclohexane. Okay, let's draw that structure. Okay, so what do we have here? We have cyclohexane. Okay, on the first, okay, let's see. On the first carbon, we have the butyl group. So here we have butyl group, and this is going to be 1, and then we say 2, 3. On the fourth one, we have a methyl group. Okay, so let's show the methyl group. And this is going to be the methyl group. So this is going to be tert butyl. And this is going to be the CH3 or the methyl group, which is equal to CH3. This one is equal to carbon attached to CH3, attached to CH3, another CH3, and this one attached to something else. Okay. I want to show those two, okay, those two on like a cyclohexane, okay, and the question is, what's the best structure for it? Okay, what's the best structure? I know size of tert butyl is bigger than size of the methyl group. So it's better to put the tert butyl in equatorial position. Okay. And how about the methyl? If it's possible, again, put it in equatorial position. Okay. So let's draw a structure. Okay. Say, forgive me. Okay, now it's not working. Okay, so I'm going to say man. Okay. Okay. So let's put the methyl, the tert butyl in equatorial position. I'm going to put it here. Okay. And remember, okay, this one is pointing down. So we're going to say this one is pointing down and is an equatorial position. So it's going to be equatorial position and it's pointing down. Okay. Down. Next. Okay. Where's the hydrogen? Hydrogen here, it will be in axial position. And that's going to be axial here, axial. So this hydrogen, it will be axial here. Okay. Now, where is going to be the methyl group? Methyl group is better to put it in this position, and that's going to be equatorial. That one, it will be CH3. Okay. This is the best structure. Okay. Why? Because you don't have any methyl or tert butyl in an axial position, and that's not going to create any strain. So the methyl group is pointing up. Okay. Methyl group is again pointing up, but it has an equatorial position and it's pointing up. Okay. So what's between this? Well, there's 4 options. I'm going to say the correct one, it will be the one that it has both of them in equatorial position. Okay, so I just showed you the answer for it. I'm going to pause here and I'm going to let you to choose the best answer for the best answer for 1 tert butyl, 4 methyl cyclohexane. I want to know which one of these is the most stable structure. Okay, thank you very much. And as I mentioned it before, this is going to be the correct answer.